So hopefully that's working. So my name's Richard Clayton from the University of Sheffield. I was really looking forward to being in Cambridge today, but I had to give some lectures to students this morning, so it wasn't possible to travel to Cambridge in 90 minutes. So apologies for being remote. So I'd like to talk a little bit about some EPSRC funded research on modelling the heart. There's been a joint initiative between Sheffield and King's College London. And in the list of authors, I've highlighted Sam Coveney because he's now a research fellow at the University of Leeds, but it's him who's done most of the intellectual heavy lifting for this project, and I want to acknowledge that. So what I want to do is to talk about one particular aspect of modelling the heart and how we can build in ideas from probabilistic modelling and uncertainty quantification. Our overall aim is to be able to build models of the heart of a specific patient. And the challenge there is that you're limited in the number of measurements and the quality of measurements that you can use for the calibration. Because you're dealing with patients, and so there's quite rightly a whole load of ethical considerations. So I'm going to talk a bit about some background, why this application is important. I'm going to spend quite a bit of time talking about how we can interpolate uncertain measurements over a manifold. I'll talk a little bit about calibration and a little bit about interpolating uncertain model parameters. And then conclude. I'm not going to touch at all on validation and verification. They're topics for another day, but happy to address those in questions. So just a little bit of background. So our hearts are electromechanical pumps where the mechanical contraction of the tissue is initiated and synchronized by an electrical activation and recovery. And in a normal heartbeat, the electrical activation starts in the heart's natural pacemaker, which is at the top of the heart here, and it spreads down through the heart, resulting in activation of the ventricles, which do most of the pumping of blood around our pulmonary system, so through the lungs and then through the rest of the body. So this electrical activation sequence is very important, and if it is disrupted in any way, we have an abnormal heart rhythm or an arrhythmia. So the one that I'm going to talk about mostly today is called atrial fibrillation, which is increasingly common in the industrialized world. It can be intermittent, so it can come and go, and it can be treated by radiofrequency ablation, which is where a cardiologist will use radiofrequency energy to damage part of the heart and stop the propagation of the electrical impulses. So the left atrium is often the place where this arrhythmia is sustained. And for the rest of the talk, I'm not going to talk about the rest of the heart at all. I'm going to just talk about the left atrium. So a little bit more about atrial fibrillation. So the picture here on the right shows a mesh of the left atrium generated from a patient. It's basically a complicated surface which we can treat as a two-dimensional surface with 5 holes in it. And what we want to be able to do using a personalized heart model is to be able to predict whether a particular pattern of radiofrequency ablation is going to be successful. The benefit of that is that we can reduce the amount of time that a procedure takes, which is good for the patient because they are undergoing the procedure for a shorter time, and it's good for the NHS because it means that procedures can be done in a shorter time period. So you can treat maybe 3 patients a day instead of 2 patients a day. So the personalization process will be based on measurements made when the patient is in a normal rhythm so the heart will be paced or stimulated using catheters that are located or placed inside the left atrium, and we can both pace and make measurements from a set of individual locations. We want to be able to interpolate these sparse measurements over this surface, and to be able to get from measurements to parameters in a model that represents the electrical activation and recovery, again, over the surface. So the model we're talking about, there's a little bit of detail on this slide. There's a link to a more detailed description. But the model is, it describes local changes in electrical potential. It's a reaction diffusion type model. So there's a diffusion term which represents how electrical activation spreads through the tissue. And then a reaction term which describes the local activation and recovery. Now, in the world of cardiac modeling, there's a whole zoo of different models that we can use to represent the reaction term. This is a simple and phenomenological model, which has two states, and it's got 5 parameters. So there's the diffusion coefficient and then 4 time constants. Now, in the clinical setting, we can't measure either of the states. We can indirectly measure the conduction velocity, so how fast the activation wave spreads through the tissue, and the action potential duration, which is how long the tissue is activated for. And we also need to bear in mind that these 2 quantities, they vary with pacing rates. And there's a property called restitution. So that's the dynamic behavior of the heart. So just to summarize some key ideas. So in the heart, electrical activity spreads over a manifold. We can model that by a reaction diffusion PDE. I haven't talked about this, and I won't say much more, but we can generate meshes for our simulations from medical images. The cardiologist can make limited measurements in a patient, and what we want to do is to use these measurements to infer uncertain model parameters and how they vary. Then we want to be able to sample these parameter fields and run simulations that we can use to predict treatment outcomes. So there's a whole bunch of uncertainties that are involved in this process. First of all, to do with the mesh itself, the representation of the heart tissue, so that the heart moves, and there's a whole sequence of uncertainties associated with imaging or getting from an image to the mesh. We've got uncertainties to do with registration of the mesh and the location of the recording catheters. There's noise, and following on from the previous speaker, we've also got discrepancies between the model and the real system. And in terms of challenges, interpolation over a manifold is something that we thought would be relatively straightforward, and it isn't when you're interpolating something that's uncertain. Nonlinear operators, I'll talk a bit more about that, but essentially, if we want to estimate a velocity, we have to look at the gradient of activation time, which is the thing we can measure. And that nonlinear operator introduces all sorts of interesting problems. And then there's the identifiability of model parameters from available measurements. So the first thing we have looked at is measurements of local activation time, which is obtained from a catheter. And typically we'll record a signal. There's a blue line or sequence of blue dots on here, which is a typical signal. It's clipped, so we haven't got the top part of the signal here. That's not unusual. And so from that, we need to build up an estimate of the local activation time at that point. And there's a couple of components to the uncertainty here. So first of all, there's the error in estimating the true activation time from the measurement. And then there's uncertainties that are to do with the registration or alignment of the mesh we're using to interpolate our measurements and the actual catheter location. So there's a little bit of detail here about the different error models that we've used, but much more detail in the paper, which is referenced on this slide. So we initially started to do interpolation of these measurements on a mesh from a patient, and we used a simple Gaussian process to do the interpolation. One of the initial problems we encountered was that we can't use Euclidean distances for the covariance in the Gaussian process because we've got a curved mesh which in places folds in on itself. So our initial work used a Gaussian Markov random field, which enabled the Gaussian field to be represented on the mesh in a probabilistic sense. And here the variance in our interpolated field accrues from the uncertainty in the measurements, which I talked about on the previous slide, and uncertainties in the interpolation. So the pictures here, on the left, we've got our estimate of the mean local activation time. In this case, the patient was being paced from this little purple spot here, which is where the shortest local activation time is, and the activation was spreading out to the blue regions. And here we've got a front and back view of the left atrium. And on the right-hand side here, we've got the variance of these estimates. And perhaps unsurprisingly, the areas with lower variance are those where we've got denser measurements. And the size of the points here, which represent the measurement locations, though the size of those circles show the observation variance that there was at each point. So we refined this method a little bit so that we could do a lot of pre-computation, so we could pre-compute some aspects of the estimate, and this involved a different approach to the covariance kernel, where we expanded in terms of eigenfunctions of the Laplacian on the manifold. The advantage is we can pre-compute all of those, and then we can interpolate our local activation times very quickly. So again, we've got some front and back views of the left atrium here with the mean local activation time and the standard deviation here rather than the variance. So the next step is to get from these measurements of activation time to conduction velocity. And that, as I've mentioned before, is not straightforward because conduction velocity is the local gradient of activation time. So one of the problems we get is that where the gradient in local activation time is small, and that happens where activation waves collide, which they do in the left atrium. So we end up with regions of very large conduction velocity in those cases. But nevertheless, we can estimate the mean of the conduction velocity. And again, here on the left, we've got our estimate of the mean conduction velocity. And then we can estimate our variability. In this case, it's interquartile range, by sampling our posterior model of the conduction velocity. And we can then invert that to determine how uncertain our estimate of conduction velocity is. So we can get from measurements of activation time to conduction velocities. And that was a bit harder than we were expecting to do. We then started to work on calibration. And what I've done on this slide is actually to summarize about 3 years' work in a small number of bullet points. I don't have time to go through all of the details, but we had a real problem with model identifiability because our model parameters do not map to uniquely observable quantities. So there's a link on this slide to a paper which describes how we've approached a solution to this problem. But the 4 little bullet points at the bottom of the slide demonstrate our approach. We first of all reparameterize the model so that observables become at least some of the parameters. We then tackled the restitution problem, which is about how 2 of these observable properties change with the rate at which the heart is being paced. And we did this by doing principal component analysis of this dynamical property, and then understanding how each of the components that were produced by PCA were sensitive to model parameters. And this allowed us to then build emulators or surrogate models of this dynamical behavior. And because the emulators are fast to compute, we could then use Markov chain Monte Carlo to estimate model parameters from observations. So just to give you a flavor of how this works, if we're aiming to recover model parameters, we can run simulations and then look to recover the parameters from simulated measurements with added noise. And on these 2 plots, we've got the log likelihood and posterior density of each of these 5 quantities, which are the reparameterized properties of the model. In each case, the black lines are the true parameter value, and we've got two plots here. And what we've done here is to look at 2 different protocols that we might be able to apply in the clinical setting, and to see which produces the tightest distribution on our parameters. And the answer is the right-hand one. But what I'm highlighting here is that we can use this as a tool to evaluate different approaches that we can use in experiments. And what is really a work in progress at the moment is then extending that to interpolating our model parameters across the left atrium. So interpolating our model parameters on our mesh so that we can then sample those parameter values, those uncertain parameters, to run simulations. So there's a couple of pictures here showing the ground truth here from an initial simulation. And then this is the model property which we've recovered, which matches very nicely actually to the ground truth. So to finish off, some conclusions and lessons learned. I think calibrating this type of model, given the kind of data that it is reasonable and ethical to collect in the clinical setting, is challenging. We found that interpolating uncertain quantities across these manifolds, that was much harder than we expected. Model identifiability is something we probably should have thought about earlier on in the project. But we are finding that these probabilistic approaches, and in particular emulation, are very powerful and useful tools. And we're already using them to design different experimental protocols. As I hinted at the beginning, this is a small part of a number of different research activities that are going on in the area of cardiac modeling. And back in 2019, before the pandemic, we ran a work program at the Isaac Newton Institute, and there's an associated issue of the Philosophical Transactions of the Royal Society, which has a whole collection of papers, which, if you're interested in application of probabilistic approaches in this area, take a look at that. So thank you for listening. I should acknowledge the different people involved in this. I've already mentioned Sam Coveney, who did much of the intellectual heavy lifting. We've had statistics expertise from Jeremy Oakley at Sheffield and Richard Wilkinson at Nottingham. And Cesare Corrado, Caroline Roney and Steve Niederer are cardiac modelers from King's College London. And this work was funded by the UK EPSRC. So thank you.
Thank our speaker, please. Can I keep it short, Danny? Sorry.
Thanks, Richard. Danny Williamson, University of Exeter. That was a really nice talk. The identifiability of the parameters is a really interesting problem, and certainly in the calibration of COVID modeling that I've been trying to do, that seems to be a big problem as well. So you have deaths, but there are lots of other parameters in there that just don't seem to move. Could you say a little bit more about the approach of reparameterizing to promote that identifiability, or do you have somewhere to point us?
I have a slide. So, I mean, there's a couple of equations here which show exactly how we reparameterize this model. What we have is two things that we can observe, so CV max and APD max, which were just obtained in terms of the other model parameters by some analysis. It turned out to be quite a simple thing. But I think the coolest thing that we did actually, or I should give Sam credit for this, was the sensitivity analysis of different principal components. And there's a reference here to the paper which describes what we did in a bit more detail. So it turned out that when we looked at the model, and particularly its dynamic behavior, we could actually describe it with three principal components, which account for virtually 100% of the variance. And then we could look at the sensitivity of these different principal components to the reparameterized parameters, if that makes sense. And that gave us a way of thinking about how to use the information that we can get to optimize the calibration, if that makes sense. Does that make sense? Or does that answer your question?
Yes. Looking at the ceiling, I think we're getting a yes. Thank you very much.
Cool.
It's getting towards coffee time. Thank you so much. Hopefully you will join us again for the discussion and summary a bit later.
Yep.
Otherwise,
I will.
I think we're going to